This is Ting-Wei Su
and Chun-Sheng Wu.
We are group number 16. Our topic to the project is cross-architectural assembly translations based on natural language processing. Let's begin. The following is our outline for today. We will begin from what is in binary translations and how it is affecting the computer architecture research nowadays. Secondly, we will start the presentation to what other survey and related work has done in the academic research, including the two approach of static binary translation will be present, including using C++, standard library parsing assembly file block by block, and applying advanced natural language processing model for binary translations. Lastly, we will conclude with our performance and future work. The introductions and motivations of this project. A binary translator is a method that allows a guest binary application to run on a host environment, thereby maintaining the binary level compatibility across different ISA. Data level parallelism, where binary translations could delegate part of the execution to different engine to execute tasks on different core to achieve. Under multi-core processor, the binary translations will allow different core to execute the task relative the best fit for processor design. For example, in order to run an applications that was compiled in RISC compiler on the Intel architecture processor, the binary translator will recompile the binary and translate instruction to host architecture. There are several methods to do this, which we can do that by compiler, interpreter, assembler, which have translate different level of language to machine code. Today, we are going to focusing mostly on binary translation. We will compare the difference between static and dynamic binary translations. Now let's discuss the translations efficiency of static and dynamic binary translations. The benefit of static binary translations is that it is recompiled and translated before execution start. This allows for heavy global optimizations and reduced runtimes. However, it will impose performance loss because of architecture heterogeneity amongst ISA. Know all the potential executed code ahead of time, which excludes self-modifying and relocatable code in the target binary. One of the most well-known static binary translation is Banshee, and which we will discuss later. The benefit of dynamic binary translations is energy saving and performance improving with specific accelerator. However, extra costs will be imposed on runtime when the system is dynamically translating. In addition, some cache miss will also be the cost during translations. Here are some background and prior work. The challenge of binary translation is that between different architectural translations, the difficulty will include dealing with mismatching ISA like ARM, load store instructions, and the mismatching register number to Intel x86. The register number and meaning in different architecture also has different meaning. In a dynamic translator, not only the runtime cache miss by context switching will expose extra cost to translation process, but also the same software, some software approach have to do by conversion to eliminate the discrepancy in endianness that leads to significant performance loss. Most of the research we survey either lies in translating the binary back to the source code or translate to the intermediate instructions. Therefore, we propose a method to directly translate assembly file. By this approach, we can exploit faster and more direct translations. The first survey is this work, which is using dynamic binary translations. This work proposed a hybrid multi-target binary translator that support code optimizations on accelerator that exploit different parallelism, as depicted in the figure HMTBT, which is in this case is a binary translator, will be serving as the translating unit at runtime, then issue the instructions to the most well-suited accelerator. In this case, the CGRA engine will exploit ILP and ARM Neo engine will be responsible for DLP. The overall performance shown 24% energy saving and 10% performance improvement with both engines combined. Therefore, the importance of dynamic binary translations to exploit parallelism on multi-core processor is substantial. In addition, and compared to with the previous study, Banshee, an instructions-accurate full system RISC-V multi-core simulator will employ the static binary translations method on RISC-V binary 5. Instead of relying on DBT at runtime, the translation stage will happen at compile time and allowing all code that a target program execute must be static, implying that all branches and functions calls must be local. First, we will take in the RISC-V ELF file and translate LLV and IR and intermediate representations. After the LLV and IR is translated, all binary will be sent to emulator to do the simulations. In the result figure, we could see that Banshee simulator scale really well up to 100 core simulations. We aim to translate ARM assembly to x86 assembly by first, string parsing, and second, neural machine translations. The advantage of our approach is that we don't have to store a huge amount of history tables for either the LLV and IR or the source code during translations. Neural machine translation attempts to adopt the deep learning algorithms in cross-architectural translations. With the help of neurons, the machine itself can translate the assembly codes without complicated history tables. That's also our goals in this project, and successfully translate the assembly codes with acceptable accuracy. Here we're going to present our method. Our first approach is by using the C++ then the library string comparison. By reading in a assembly file, we could parse a file line by line. After checking the opcode and operands in each line, compare the logic with the history tables to see if the block of code could be translated. Upon finding the matching logic in the history map, we move on to the next block. If not, then an error will occur. Here comes the limitations in this approach. Every logic has to be inscribed in the history map table before translating. Therefore, after realizing the limitations, an advanced method to intelligently detect the translated assembly with an NLP model is presented. We will have Chun-Sheng to elaborate this detail.
Hi guys, I'm back. Okay, this is our overall structure of the neural machine translation model. The left four sections are the data preprocessing, which handles the raw data. It can process the input assembly code. It is the x86, it is the ARM assembly code in this project into tuples, which is spatial forms in TensorFlow that can be fed into the natural language processing models. In the followings, I will introduce the way we design the NLP models and the algorithm we utilized and compared with binary translator. In the very beginning, we should discuss the redundant elements in the assembly code, like the end of line and extra unnecessary spaces. After removing those stuff, we split the lines into code blocks. The standard how we split it is when the code encountering loop or branches, it forms the code blocks as a sequence. It's like a sentence in English. The bottom left graph shows how the code looks like after the split. Well, after that, because the root numbers of x86 and ARM are not identical, we have to shuffle the codes and make them into groups with the same numbers. Here, we apply greatest common denominator to define how many groups there are. We keep padding spaces in the tail of each ARM code block when the GCD is greater than the root of characters in codes. In this project, the number is approximately 3,700, I remembered, and the last step, we should tokenize the reorganized code blocks and form tuples which are needed to compose a training dataset. This slide shows the specs about our final dataset. The initial code blocks of each structure are increased due to shuffling reorganizations. Code blocks number increased from 1402 and 788 to 3709. And there are 2,500 more characters in ARM. Okay, then let's keep going to the detail of NLP models. There are 3 different NLP models we used in this project. Recurrent neural networks is the first technique fit with text generation. It organizes recursive neurons to learn the hidden logics. It's like a baby to learn the grammar in human languages. But RNN has significant problem about gradient updating with small sample benches. Based on this, long short-term memory named LSVN is devised with input forget and output gets. The ratio where the signal will be discarded is defined by stored weights. Therefore, LSTN facilitates the performance but heavily increase the computing loading in the same time. Therefore, gated recurrent unit comes out and further replace the input and output gets with update gets to have a better balance. After the introduction of the NLP models, let's talk about the structure we used. Encoder attention decoder is proposed in 2015 to handle the multilingual machine translation. This structure resolves the problem of various sequence lengths. In case that assembly code blocks usually have various characters inside, we decide to choose the structure as our final structure. Encoder and decoder are both implemented by RNN, LSTN, or GRU layers. At the outset, encoder processes the input sequence and passes it to the attention layer. Attention layer produces context vectors and concatenate them with the input from encoder. Decoder subsequently output the target sequence through the input vectors and dominate weights from attention layer. All right, after finish our structure, then let's talk about our performance evaluation. Well, due to the computing ability limit, we set up the initial hyperparameters as follows. We firstly train the 3 different models with 100 epochs to determine which one is better and to use on the comparison with the conventional binary translator. While the training procedure, the checkpoints which reach the lowest loss is always stored. By doing so, we can always keep the best one without overlapping, the best checkpoint, I mean. There are the laws between the models. From the left to the right, there are the laws about simple RNN, LSTN, and GRU models. They achieve great performance and low sparse cross entropy loss in training. However, we can see that simple RNN and GRU models are slightly better than LSTN models. Besides the performance, we compare the training cost time as well, since the translation efficiency has a critical role in this project. Fewer execution time means the better translation efficiency in actual situations. Obviously, as the LSTN and GRU models cost much less time than simple RNN model. So combines the result of performance, we decide to employ the GRU model as the neural machine translator to compare with the conventional binary translator. But before we start the comparison, to achieve desired translation accuracy, we train the GRU model with 500 epochs. It reaches the loss to -4 power of 10. Training and testing accuracy above about 93%. That is means overfitting or underfitting are not happened. Let's look at the translation time. GRU model costs about 1.3 seconds to translate the testing data set, which are composed of 742 code blocks. And the translation time with the whole data set is about 2.1 seconds. And let's look at the other side. The static binary translator with history table spends nearly 2.3 seconds to finish translating the whole data set. From here, we can conclude that neural machine translation definitely has the potential to outperform the binary translator we use nowadays. And let's go to our conclusion. Although it costs much time to train a robust neural machine translation model with sufficient data set, our experiment exhibits its power to efficiently execute cross-architectural translation. We believe, once the dataset is large enough, the model's accuracy can reach 95, 96, or even 99%. Therefore, we should not put much effort on adjusting or revising the produced codes. The graph below is the execution time in binary translation and neural machine translator. The reduced time gives us a promising future on neural machine translation methods. And here we point out some ways beneficial to enhance the model's performance. The first one, and also the most important one, is how to preprocess the raw data and maintain the logic semantic equivalence in the meantime. Some instructions, for example, conditional branches need register values to determine the following instructions, but we cannot successfully keep them in this project. It will be a great lesson about how to keep them. Other techniques like redundant information elimination and pending space strategy are also methods to help make the codes keep semantically equivalent. Except the preprocessing part, there is some points we can do on the NLP models. Refer to some newly published paper to customize the attention layer and enhance the NLP models are able to help the models perform better. Okay, that's the end of our project presentation. Thank you all for watching our presentation. Thank you.